Hey folks, welcome back. We're going to continue our discussion of infectious disease models, and we've been talking about the SIR model for a few days now. In the last video, we introduced two important parameters, the basic reproductive rate and the effective reproductive rate. And the basic reproductive rate you can think of as the number of infections that are caused by a single infectious person in a completely susceptible population. So if everyone in the population, except that one infected person obviously, if everyone in the population is susceptible to the disease, then this is the number of infections you expect to result from that one person, because that one person's running into kappa people per day that they could potentially infect. They're sick for gamma days, and so you multiply that by the probability of infection and you get the total number, or the fraction of interactions that lead to infections. Then you get the total number of infected people. And you see you can relate that to the A, the B and the N. The N's the total population, but A and B are the constants that appear in our model down here. So the effective reproductive rate is what happens when not everybody in the population is susceptible. Right? So not everybody in the population is susceptible means that I take the basic reproductive rate, there it is, the R sub 0, and I multiply it by the current fraction of the population that are susceptible. And that will tell me how many infections I expect at the given moment. So in the previous example, we talked about the initial number of susceptible people because we were thinking about the starting point. But in general, you can define this effective reproductive rate at any moment in the course of the disease spreading in the population. So this S is a function of time, everything else is a constant unless we change it, right? Because these constants are related to the A's and the B's. Here they are. These constants are related to the A's and B's. So if we can change them, then we're changing the R naught. But our condition for a disease to become an epidemic was that the effective reproductive rate is greater than 1. So let's have a look then, or I should say before I continue, this R naught, you can really think of it as the rate at which the disease is spreading at the beginning of the epidemic, because at the very beginning of the epidemic is when you expect most of the population to be susceptible. In other words, at the beginning of the epidemic, you expect the number of susceptible people to be everybody except the one infective person. So when you take that ratio, if N is large enough, that's pretty much 1, right? And if the quantity in this bracket is 1, in other words, N minus 1 over N, as long as N's big enough, this is 1. And so this effective value at the beginning is equal to the basic reproductive rate. So we think of this basic reproductive rate as the rate the disease spreads right at the start of the epidemic. So we're going to think about what happens right at the very beginning of the epidemic. And at that moment, you expect the number of infected people to be 1, right? The number of recovered people to be 0. And the number of susceptible people is everyone else in the population, which is N minus 1, because I expect these two to add to 1. But to make some progress and to make an approximation, I'm going to imagine that N minus 1 is approximately the same as N. All right? And then I'm going to plug it into this equation down here. And I'm going to assume that the disease has an R naught that's given by, AN over B, and R naught is some, spread rate of the disease. And if this is an existing disease that we know, or a disease where we've previously encountered, we know what the R naught is. So we can think of the R naught as being a known quantity almost. And so if I know R naught and let's say B, then I could calculate A. And so I could find the parameters of this model by knowing a little bit about the properties of the disease. And remember that B is 1 over gamma. Gamma is the number of days that you're typically sick with the disease, how long it takes to recover. So B is 1 over gamma, so it's the recovery rate. Roughly, it's the fraction of people who recover on a given day. And so I typically would know B from observation, and R naught is something we know about diseases. And so that would let us find A. So let's just think about what happens here. I'm going to write down this differential equation, and I'm going to focus on this equation because at the beginning of the disease, what I'm really focused on is the number of people who are infected. And I'm going to say that at the beginning, that the S value is approximately equal to N, right? It's basically the entire population. If N is large enough, then subtracting 1 from it really is not changing anything. So the rate of change of I is given approximately by this expression. A times N, the number of susceptibles, I'm just plugging that in, and b minus I minus bi. And so this is a separable equation because this I can factor some things out. And so I factored the I out, there's an I in each of these terms, but I've also factored the b out. And what that's left me with is this term, an over b. And an over b is our R naught. And so I've rewritten this differential equation in this simplified form at the beginning of the epidemic. Now, this is an exponential, this is a separable equation. We can separate the I from everything else. Everything else is a constant. And so we end up with an equation that we can integrate with respect to t. And when you do that, you find that I is an exponential. It's a function of I sub 0, that's the initial number of infected people, e to the power of b R naught minus 1 times t. And we know this is the initial number of infected people, so that's going to be 1, right? Our initial condition here was 1. That's the initial number of infected people. And there's a bit confusing in this notation. Let me write this as I of 0 because R sub 0 isn't the number of removed at time 0, because that's 0. R sub 0 is the basic reproductive rate. So you can see very clearly here, I hope, that if R sub 0, the basic reproductive rate, if that's bigger than 1, then this quantity is positive, B is positive, and so this is exponential growth. But if R sub 0 is less than 1, then we see exponential decay. Because if R sub 0 is less than 1, then this quantity in the brackets is negative, times B, which is positive, times T, which is positive. Right? This is for time greater than or equal to 0. So we see exponential decay. So this tells us two things. At the beginning of an epidemic, if the basic reproductive number is bigger than 1, our threshold essentially is bigger than 1, we see exponential growth. It's not just that the number of infected people increase, but the number of infected people increases exponentially. And then if the basic reproductive number is less than 1, the number of infected people decreases exponentially, which is a good thing, right? The number of infected actually decreases as quickly as you could hope. Whereas if R naught is bigger than 1, it's increasing more quickly than you would want. Because if you remember, exponentials increase more quickly than any polynomial. So no matter what power polynomial, the exponential will always increase more quickly eventually. So this gives us an idea of what happens at the start of the epidemic. The answer is we get exponential growth if R naught is bigger than 1. So we see here a count of the number of confirmed, so tested COVID-19 cases in the US in early March. And we know from our model that we would expect exponential growth in this early period. So let's do a simple calculation here. You know, I could take this data and try and fit an exponential to it. But let's be even more simple-minded here. Let's look at these 2 days, 1 week apart, and let's think about what happens in that period. If I started on March 1st and went to March 8th, 7 days later, and this was the change in cases, then I would take I of 0 to be 69, and 7 days later, I of 7 is going to be 433. So there's the two values that I'm pulling from the table here. And we know B, right? We can estimate B because B is 1 over gamma, right? And gamma is the number of days it takes to recover from the disease. So the number of days you're actually infectious. So let's just assume that that's 14 days. It's not entirely clear for COVID-19 whether you're infectious for 14 days, whether you're infectious longer than that, but people are typically sick for at least 14 days, or the quarantines are being set so that people are kept away from others for 14 days after they see symptoms. So that's a good value to take, at least for this calculation. So at 7 days, we can plug into this system and we see that 433 must be 69. E to the B, we know it's 1 over 14. R naught minus 1. That's what we're going to calculate because we're doing this after 7 days and we're going to solve for R naught. So solving for this thing, we can solve for R naught and rearranging, we get a term like that, which in this case is our gamma was 14 days. So this is 14 over 7. And this is the natural log of 433 over 69. Just solving that, you'll see that this is what you get. And that gives us an R naught of approximately 4.67, which is large, right? That's definitely bigger than 1. This is definitely suggesting that the disease is going to spread. Now, something worth bearing in mind here is we know that testing has been pretty, non-existent to poorly organized in the US. Certainly in March they weren't testing for many cases. So there's a question of whether these numbers are a reasonable reflection in the actual growth of the disease, or whether these numbers are growing quickly, more quickly here than you would expect, because the testing is slowly ramping up. So let's do another calculation where we do something similar, but we'll do it a month later where there's a bit more testing and maybe the testing is more consistent. So now let's do the same calculation, but this time let's look in April where maybe the testing was more consistent, and so this change is actually through the real number of infections that have appeared rather than additional testing percentages, right? Because if in March, at the beginning of March, we were testing, 10% of the people, but by the end of the first week of March, we were testing 20% of people. We're picking up new people who we wouldn't count before, so it doesn't represent a true rise in the number of disease cases. So maybe by April, that would be more reasonable to say that we did, and assuming again that we've got an infectious period of 14 days, we've got a 7-day period here, and then we just need to plug in the difference in the number of infections or the ratio of the number of infections in those two times. And notice that that's pretty close to 2. It's a bit bigger than 2. So this is close to the doubling time for the number of infections in April. And if we calculate that, we find that the R0 is about 2.49. And remember, this R0 is only usable, it's only reasonable to talk about R0 at the beginning of the disease. So this really needs to be growing exponentially still in the early phases for this to be a reasonable estimate of R0. But in fact, that is consistent with the observation. Right? The R0 in the US right now is estimated, or for the disease in general, is estimated to be in the 2.2 to 2.5 kind of range. So that's definitely a consistent R0. And so we're seeing that come out of our simple model. And remember, our simple model here, we've simplified to the point of we're only looking at the very beginning of the outbreak. This is not a solution to the SIR model. This is an approximate solution in the very early stages when the growth of the number of cases is entirely exponential. So in that case, with those assumptions, what we're seeing is an R0 in the US of about 2.49 in early April. So let's have a look at how we might reduce the effective reproductive rate and slow the spread of the disease. So we know the effective reproductive rate is what governs the spread of the disease. Once we get an effective reproduction rate that's less than 1, the rate of change of the number of cases is going to be negative, and we should start to see exponential decrease in the number of cases. So we really want to make that effective reproductive rate less than 1. How would we do that? I'm relying here on an article by Howard Weiss that appeared in 2013. I've adapted some of his suggestions. And his first suggestion is to reduce the number of contacts. Literally, we're going to go through this expression here, and we're going to talk about how we can make it less than 1. Well, one way to do it is reduce the value of kappa. Kappa is the number of contacts that each person has on a given day, and one way to reduce that is through self-isolation and stay-at-home orders, right? The idea that we're going to quarantine ourselves, we're going to reduce the number of people we see on a given day, because a population, and again at the beginning we talked about this, but a population, this is a cultural number, a population in general is going to have an average number of contacts per person per day. In an extraordinary situation like this, we can reduce that number of contacts by staying home, by self-isolating as far as possible. And reducing kappa, I mean, it's one of the factors here. If I halve kappa, I halve the effective reproductive rate of the disease. The second factor is to reduce the TOR. The second approach is to reduce the value of the TOR in the expression. And TOR is the probability that we're going to transmit it. It's the fraction of interactions that actually lead to a new case. And you can reduce that by hand washing, right? If you wash your hands more, you're less likely to pass the disease on. If you wear a mask, you're less likely to breathe on people. The interactions that you're having are less likely to be transmitting the disease. That's the goal of reducing TOR. So that's the second thing we can reduce. The third case, we might try to reduce gamma. Gamma is the duration of the infection, right? So medical care, antivirals, that kind of thing might be able to reduce the length of your infectious period. Now, for COVID-19, it doesn't seem like we have a way to do that right now. I'm not sure antivirals are effective. I don't have any expertise on that. It seems like the medical care is not helpful at this point. There's nothing that can really be done apart from the first two, which are isolation and reducing the probability it'll be transmitted through hand washing and masks and that kind of thing. But for a general epidemic, that's another way of approaching reducing the effective number of reproduced cases per person. Of course, the last one is to reduce the actual fraction of the population that could get the disease. That S over N is the fraction of the population that's susceptible to the disease. So one big idea is to reduce the fraction of people who are actually susceptible. And the way to do that, most safely, is using a vaccine. Right? The number of people who are susceptible is going to be reduced anyway. Our model predicts, remember, that quantity is decreasing for all time. But the fact that that's happening is because people are getting sick. Right? And I didn't mean R, I meant S. The number of susceptible people is decreasing in the model, but that's because they're getting sick. We don't want that. We want to develop a vaccine which reduces the number of susceptible people without actually causing illnesses and without actually leading to deaths. And so these kind of strategies, notice how these strategies are coming straight from the mathematics. They're coming straight from the effective reproductive number. We're looking at what that thing is and we're reducing each of those quantities. Let's talk a bit more about a vaccine. Well, let's hope in the near future that a vaccine is developed for this COVID-19 disease. Let's hope that sometime in the near future we can launch a vaccination program and get, let's say, the fraction rho of the population vaccinated. In other words, if rho is a half, we're talking about 50% of the population is vaccinated. Half of the population would get this vaccine. What we need for protection from an epidemic is RE to be, R sub E, the effective reproductive number, to be less than 1. Because remember, the whole idea of this is if the effective reproductive number is less than 1, then the rate of change of the number of infected people will decrease. So even if there are infected people in the community, as long as the effective reproductive number is less than 1, that the number of infected people is going to decrease rather than increase. And that's exactly what we want to avoid. Well, if we've vaccinated the fraction rho people in the population, then how many people are left in the population that are susceptible? Well, we started off with S sub 0 people in the population, let's say, and we vaccinate rho of them. So there are now rho times S sub 0 people who are actually susceptible. So in our vaccination program, we're going to go out and we're going to find all the susceptible people and we're going to vaccinate some fraction rho of them. Right? So after the vaccination process, there are rho times S vaccinated people. So let's say rho is 70% or 0.7. We vaccinated 70% of the susceptible population. So the number of vaccinated people would be rho times S, so 0.7 times S. And the people who are still susceptible would be 1 minus rho times S. Now you've got the same number of infected people wandering around, but they're coming into contact with a lot fewer susceptible people than they were previously. And what that means is we've changed the effective reproductive rate. We've got a new effective reproductive rate, which has the old population of susceptibles replaced with this new population of susceptibles after the vaccine. And again, for this to avoid an epidemic, we want it to be less than 1. Now, the disease itself had some sort of effective reproductive rate, right? So that effective reproductive rate for the disease, we could work out at the beginning. It was this thing where S sub 0 was effectively the full population to begin with. And so you can still see that quantity here. So what I've got is exactly the same quantity that I had before. Oh, look what it is. There's our effective reproductive rate for the disease itself, which is essentially R sub E or R sub 0 at the beginning of the disease are the same. And then we've picked up that 1 minus rho factor and we have to have it less than 1. So what I'm imagining is magically one day I come in and vaccinate some percentage rho of the population. Before I did that, it was right at the beginning and the disease was spreading at some effective reproductive rate, R sub E. And near the beginning of the disease, R sub E is about the same as R sub 0, the basic reproductive rate. And so this thing in purple here is R sub E or R sub 0, whichever you want to call it. But I magically reduce the number of susceptibles, which is introducing that factor of 1 minus rho. And so I can actually solve that for rho, right? If I want this to be less than 1, I want it to be less than 1 because I want to avoid the disease becoming an epidemic. So this quantity has to be less than 1 to avoid an epidemic. If we rearrange this inequality, we can say that rho has to be bigger than 1 minus 1 over R sub 0 for us to avoid an epidemic. Think about what that means. This is the criteria for the vaccination program to be successful. Because a successful vaccination program is going to avoid the disease becoming an epidemic, which means we need rho to be bigger than 1 minus 1 over r sub 0, r naught. R naught is our basic reproductive number. It's a property of the disease. This is what's known as herd immunity. You've vaccinated enough of the herd, enough of the population, to avoid the disease becoming an epidemic. Right? As long as you vaccinate this proportion greater than 1 minus 1 over r of the population for a given r naught, you will end up with a decreasing number of infectious cases. And that's the key to avoiding an epidemic. So this is our criteria for herd immunity. So to avoid an epidemic, we want to vaccinate this fraction of the population at the very least, right? 1 minus 1 over r naught. So for COVID-19, we know that r naught is, say, 2.29, which is about what we saw before as well. Then the minimum fraction of the population that we have to vaccinate is 1 minus 1 over 2.9, which is about 0.56. So we'd need to vaccinate 56% of the population to establish herd immunity and end the epidemic, right? And that's using our very simple model. So again, this is an estimate. I'm not giving public health advice here, but we certainly see from this simple model that we can capture a lot of the ideas that the more complex models that the professionals are using to answer these questions. They're approaching things in a similar way, obviously in more sophisticated models. It's worth noting before we go, though, that for measles, which has an R naught, if you remember, between 15 and 18, let's say it's 15, let's take the better case there, that's going to give us 93%. So for measles, even if you take the best case scenario for the R naught values, you're going to have to vaccinate 95% of the population. For diseases like measles, it's so hard to establish herd immunity because it takes such a large fraction of the population to be immunized against the disease to protect everybody. If R naught is relatively lower, then herd immunity will kick in at a lower level of vaccination, which, by herd immunity here, I'm saying the disease will then decrease in number of infectious cases for all time after that. So hopefully this has given you an idea of how we can use these SIR models to sort of understand the beginning, the end, the sort of maximum of our diseases, and get an idea about how herd immunity mathematically comes about. Talk to you soon.